In this video, we will go over how to calculate oxidation numbers, which are important for oxidation reduction reactions. So let's briefly describe what an oxidation reduction reaction is. It is also known as a redox reaction. So an oxidation reduction reaction is a combination of an oxidation half reaction and a reduction half reaction. So in an oxidation half reaction, we actually lose an electron. So an electron gets lost. And typically in half reaction form, that free electron gets liberated and is subsequently on the product side of the equation. As an example, in order for sodium to become sodium plus 1, it loses 1 electron. Now, opposite to that, its natural partner is a reduction. In a reduction half reaction, we gain electrons. So in order for sulfur S to become the sulfide ion, S minus 2, we must gain 2 electrons. So an oxidation is an oxidation is a loss of an electron. A reduction is a gain of an electron. When you combine those two together, you get an oxidation reduction reaction, where element A or substance A gets oxidized to substance B. In turn, element or substance C gets reduced to element or substance D. So it's a couple. A redox couple is a combination of an oxidation and a reduction. Joining them together, you get the full oxidation reduction reaction. Now, in order to actually perform an oxidation reduction reaction, you must change the oxidation state. You must change the oxidation number. So as an example, the oxidation number here of sodium is 0. It's changed to plus 1. Sulfur is 0, it gets changed to minus 2. So the change of oxidation numbers is important in an oxidation reduction reaction. Now, in order to actually memorize what an oxidation is and not to confuse it with a reduction, we often use the mnemonic LEO-GR. Lose electrons oxidation. Notice you lost an electrons or electron here on the product side. Gain electrons reduction. So when you gain an electron, it's on the reactant side of the equation. One more thing I want to point out is the balancing of charge. We want to balance our chemical equation as always, but we also want to balance our charge. So sodium here has no charge. So on the reactant side, the charge is 0. On the product side, the charge is plus 1, minus 1. The charge is 0. So reactant side, the charge is 0. Product side, charge is 0. We are balanced. Look at this half reaction. On the reactant side, the charge is minus 2. On the product side, the overall net charge is minus 2. So here we're charge balanced here, minus 2 on the reactant and product side. Here we're balanced on charge 2 as well, 0 on the reactant side, 0 on the product side. So before we actually go in depth into oxidation reduction reactions, we have to recognize oxidation numbers. So an oxidation number is just an assignment based on certain rules. We look at a compound, and then we give each element of that compound a number. Okay, so it is an assignment. And that assignment of a number can change. It really depends on the chemical compound. So as an example, if you look at nitrogen, the oxidation number in nitrogen and nitrate, these two are ions, nitrogen monoxide and nitrogen dioxide, the oxidation number of those nitrogens are different in these 4 states. So nitrogen can have a wide assortment of oxidation numbers. As you know, transition metals are very famous for having a wide array of charges, have a wide array of oxidation numbers. So let's go over the rules of oxidation numbers. So the first rule is that if the number is standalone by itself, it's 0. Okay, so first of all, these are not compounds, these are elements. So O is the diatomic element, S is a form that's S8, iron is by itself, sodium is by itself, cobalt, chlorine diatomic is by itself. Standalone or base elements gets an oxidation number of 0. The second rule here has to do with the alkaline metals and the alkaline earth metals, group 1 and group 2 respectively in the periodic table. Okay, they carry the charge, that is the oxidation number, equivalently. So we all know group 1 elements have it as an ion, a plus 1 charge. Group 2 elements have a charge as an ion as plus 2. So group 1 will be plus 1 oxidation number, or oxidation state. Group 2 will be plus 2 oxidation state. So that's rule number 2. Rule number 3 has to do with oxygen. So oxygen in this course will have an oxidation number of -2. We'll keep things very simple, and in the most simplistic sense, oxygen will have an oxidation number of -2. There are situations where it could be a little bit different, but those are rarities, and we will not cover them in this course. Fluorine as a halogen will always have an oxidation number of -1. Okay, not all halogens, for example, chlorine and bromine can have differing oxidation numbers, but fluorine will always be -1. So that is an absolute. So anytime you see a fluorine, recognize that it has an oxidation number of -1. Anytime you see an oxygen, at least in this class, no tricks, it will have an oxidation number of -2. Along the lines of that, this is HBr, should be capital, hydrobromic acid. Along those lines, hydrogen will have an oxidation number of +1. So again, this is the 99% rule. 99% of the time, hydrogen in this course will have an oxidation number of +1. For those of you that are a little bit more keen, a hydrogen, when it's bound to a metal, that's called a hydride ion. And in that very specific instance, it will have an oxidation number of -1. But for this course, we just need to recognize that hydrogen will be +1, fluorine will be -1, and oxygen will be -2. The final rule has to do with the sum. So when we have a chemical compound which exists as some combination of 2 or more elements, the sum of the oxidation numbers will have to equal to the sum of the charge. So as an example, the hydroxide ion, which we learned in our flashcards, has a total charge of -1. So the oxidation number of oxygen plus the oxidation number of hydrogen has to equal -1. And we kind of know that because we memorize 99% of the time oxygen will be -2 and hydrogen will be 99% of the time +1. So -2 + 1 is -1. Nitrate ion as an example. So do not get confused. Nitrogen plus 3 oxygens, okay, because there's 3 oxygens here. Nitrogen plus 3 oxygens, that whole unit has to equal -1. Now we already know from the previous slide that we can guess with reasonable confidence that the oxidation state of that oxygen is going to be -2. So really it's going to be N plus 3 times the -2 oxidation state of oxygen times 3 will equal to -1. So if you do that math, it will be N minus 6 equals -1. Here, the nitrogen has an oxidation state of +5. KMnO4 consists of 3 elements. So K, which is going to be +1. Okay, that's something we know from our rules. Mn is a transition metal. Really, the manganese element really don't have an inkling of what it will be. And oxygen is going to be -2. So that's, again, we're not going for rarities 99% of the time. You would be correct in saying oxygen will have an oxidation state of 0. Now, all of that has to equal to 0. Okay, so because there's no charge, K plus Mn plus 4O has to equal 0 because there's simply no charge, contrary to here where the total charge is -1 and the total charge is -1 here. So Mn here has an oxidation state of actually +7, where you do 1 minus 8 is -7, but you move it to the other side, and then you'll find that manganese has an oxidation number of +7. Now, when you do an oxidation number, recognize that it's important you put the charge. So +7 here or -1 here. You can't just write 1 or 7. It's got to be either -1 or +7. So those are the 6 rules that involve oxidation numbers. With those oxidation numbers, we can actually balance oxidation reduction reactions, which is some sort of change in the oxidation number of an element in going from reactants to products. That is something that we will do. Balancing oxidation reduction reactions is something we will do later on in the course.